In October 2024, the New Journal of Physics published a paper by a group of scientists from the United States and Canada who seemingly demonstrated the possibility of cold nuclear fusion, albeit so far purely theoretically. Cold nuclear fusion is the philosopher's stone of modern energy science. Unlocking its mysteries could literally usher in a new era for humanity, marked by cheap, environmentally friendly, and universally accessible energy supplies that would remain virtually inexhaustible, even from the broadest historical perspective. Over the past half-century, scientists have explored numerous methods to achieve cold nuclear fusion in practice. Some even claimed success, but none of these assertions have ever been confirmed by independent verification. The situation is further complicated by the actions of outright fraudsters, who claim to have initiated cold nuclear fusion using secret techniques they refuse to disclose. As a result, the modern scientific community predominantly takes a skeptical stance toward the very concept of cold nuclear fusion. This has gone so far that researchers in this field now avoid using the overly discredited term, preferring instead to describe their work as studying low-energy nuclear reactions. In such a climate, even a purely theoretical conclusion suggesting that cold nuclear fusion is possible in principle could shift perspectives and invigorate research in this area. And then, who knows, perhaps the feasibility of cold nuclear fusion will eventually be proven not just in theory, but in practice. Before diving into the specifics of the paper, let's take this opportunity to discuss what nuclear fusion actually is, how it releases energy, and why there is a distinction between cold nuclear fusion and hot, or thermonuclear fusion. Let's start with the basics. If we take a proton and a neutron and bind them together to form the nucleus of a deuterium atom, a heavy isotope of hydrogen, we'll observe something remarkable. The mass of the resulting nucleus will be less than the combined mass of the proton and neutron. These particles, collectively referred to as nucleons, exhibit what is known as the mass defect. Why does the mass defect arise? Its roots lie in general relativity and are linked to the famous formula E equals mc squared, which connects an object's mass to its energy. That is, every object possesses energy because it has mass, and vice versa. The fact that an object has energy implies it must have mass. However, this statement is true with certain caveats, which we've discussed in one of our earlier videos. In this case, it holds true, and the mass of a composite atomic nucleus must equal its energy divided by the square of the speed of light. The energy of the atomic nucleus equals the rest energy of the nucleons composing it, but we must also add their total mechanical energy, i.e., their kinetic and potential energy. The potential energy of attractive forces is always negative, and for nucleons to stay bound in a nucleus and not fly apart, the magnitude of this negative energy must always exceed their kinetic energy. In other words, the total mechanical energy of nucleons in a nucleus is always negative, and the nucleus's total energy is thus always less than the total rest energy of its constituent particles. In other terms, the mass of the nucleus is always less than the combined mass of the nucleons within it. Now let's imagine taking two deuterium atoms and fusing them together to create a nucleus with two protons and two neutrons, the helium-4 nucleus. We find that the helium-4 nucleus weighs less, not only than the total mass of its nucleons, but also less than the combined mass of the deuterium nuclei. Why? It's not hard to understand. The deuterium nucleus consists of one proton and one neutron, which attract each other via the strong nuclear force. In a helium-4 nucleus, there are 4 nucleons, each attracting every other nucleon. Consequently, the binding energy of the nucleus is larger, and its total energy and mass are lower. The excess energy will be released into the environment in some form. In this case, it's released as a quantum of electromagnetic radiation. However, this energy turns out to be quite significant. In such a reaction, the energy of the quantum by which the nucleus sheds its excess energy is as much as 23.85 million electron volts. This corresponds to high-energy gamma radiation, though such photons are rarely produced. Instead, the resulting helium-4 nucleus most often undergoes decay, losing either a proton and becoming the super-heavy hydrogen isotope tritium, or losing a neutron and turning into helium-3. In both cases, the nucleus can release energy as the kinetic energy of the particles, which essentially just fly apart. However, we'll talk in more detail another time about how and why certain nuclear reactions occur, or don't occur. For now, what's important is this. Reactions that create more complex nuclei from simpler ones while releasing energy are known as nuclear fusion reactions. It turns out that if we were to cause all the deuterium on Earth to undergo fusion, we'd release energy amounting to approximately 10 to the power of 30 joules. At humanity's current energy consumption rate, that amount of energy would last for about 30 billion years, and that's just deuterium. In theory, nuclear fusion could be achieved with virtually any atoms from the first quarter of the periodic table. This means nuclear fusion is indeed an almost inexhaustible energy source. If only we could reliably make atomic nuclei undergo such reactions. And this is exactly where the challenges arise. The strong nuclear force is effective only at distances smaller than 10 to the power of minus 15 meters. So for these forces to take effect and bind nuclei together, the nuclei must approach to within this distance. However, since nuclei have a positive electric charge, they repel each other. To bring them close enough to fuse, they need kinetic energy at least equal to the work required to overcome this electrostatic repulsion. Or, as it's often called, the Coulomb barrier. The height of this barrier decreases with lower nuclear charge, meaning that nuclei with fewer protons, such as hydrogen isotopes, fuse more easily. Nevertheless, even for hydrogen isotopes, the required kinetic energy is hundreds of thousands of electron volts, corresponding to temperatures of hundreds of millions of degrees. In other words, to initiate nuclear fusion, matter must be heated to at least hundreds of millions of degrees. This is why we refer to thermonuclear fusion, fusion at extremely high temperatures. Of course, heating matter to such temperatures and maintaining it in this state is no trivial task. That's why, even after more than half a century of experiments in nuclear fusion, we have yet to achieve reactions efficient enough to produce more energy than is consumed in initiating them. But is it always necessary to heat matter to hundreds of millions of degrees to trigger a thermonuclear reaction? We know for certain that the answer is no. For example, in the core of our Sun, thermonuclear reactions occur successfully at much lower temperatures, around 15 million degrees. To understand how this is possible, we must remember that we're dealing with atomic nuclei, which are extremely small objects governed by quantum mechanics rather than classical mechanics. In quantum mechanics, phenomena sometimes occur that would be impossible according to classical physics. For example, in one of our previous videos, we discussed quantum tunneling, a highly paradoxical phenomenon in which quantum mechanical objects can, with some probability, overcoming potential barriers that, from a classical perspective, their kinetic energy should be insufficient to surpass. The same applies here. While most hydrogen nuclei in the thermonuclear core of the Sun lack the energy needed to overcome the Coulomb barrier, some of them occasionally manage to do so by tunneling through it. And although this happens with only a tiny fraction of the nuclei, the number of atoms in the Sun's core is so vast that even this small fraction is sufficient to generate enough energy for the Sun to illuminate and warm us. The lower the temperature and energy, the lower the probability that two atomic nuclei will succeed in undergoing a fusion reaction. However, this probability never drops to absolute zero. Even under normal room temperatures and pressures, or even at lower temperatures and pressures, this probability remains non-zero. In other words, nuclear fusion reactions can still occur under normal conditions, albeit extremely, extremely, extremely rarely. It has been calculated that in a deuterium gas at room temperature and pressure, fusion reactions occur with a frequency of approximately once every 10 to the power of 64 seconds for each pair of atoms. This is an astoundingly low frequency. In 1 cubic meter of such gas, which contains roughly 10 to the power of 25 atom pairs, you would need to observe this volume for about 10 to the power of 40 seconds, or 10 to the power of 32 years, to witness just one fusion reaction. For comparison, the age of the universe is roughly 14 billion, or 10 to the power of 9 years. In layman's terms, this means that such reactions almost never occur. But almost never doesn't mean never. So, is there a way to increase the likelihood and frequency of such events? Certainly, yes. And the authors of the paper we're discussing today decided to analyze these methods and estimate whether it's possible to achieve a reasonable frequency of reactions. Say 1 every 10 to the power of 23 seconds, which would result in about 100 events per cubic meter of gas per second. From an energy perspective, this is still vanishingly small, yet it would be sufficient to detect such a reaction and confirm that cold nuclear fusion is, in principle, possible. And from there, as they say, it's a matter of technical refinement. To even reach the detection threshold for nuclear fusion reactions, the probability of such an event under room conditions must be increased by a factor of 10 to the power of 40 orders of magnitude, which seems like an utterly insurmountable task. Nonetheless, the authors of the paper argue that it may not be entirely impossible. As mentioned earlier, the force of electrostatic repulsion prevents atomic nuclei from coming close together. However, this repulsion can be reduced by balancing the positive charge of the nuclei with the negative charge of other particles, such as electrons. Electrons will be attracted to the nuclei, forming a kind of screen that compensates for the electric field of the positively charged nuclei. Thanks to this screening effect, the nuclei can approach each other more closely, increasing the probability of spontaneous fusion reactions. And this is not just theoretical. This effect is applied in practice. By embedding deuterium atoms into heavy metals, such as palladium, and forming hydrides of these metals. Recall that the crystal lattice of any metal is primarily composed of the metal's atoms, which have lost some of their electrons and become positively charged ions. The freed electrons create an environment that fills the spaces between the ions. Physicists refer to this environment as an electron gas, because each electron is simultaneously attracted to multiple positively charged ions. These forces balance each other, allowing the electron to behave almost like a free particle. Now, if hydrogen atoms are embedded into this crystalline lattice, the electron gas acts as a screen, enabling the nuclei to come closer together and increasing the likelihood of fusion reactions. This phenomenon is used in practice to create compact neutron sources. A fragment of a metal hydride, more precisely, a metal deuteride, saturated with deuterium atoms, is bombarded with a stream of deuterium or tritium nuclei accelerated by an electric field. Thanks to the electron screening effect, nuclear fusion can occur at much lower kinetic energies of the incoming nuclei, allowing the use of relatively weak fields and eliminating the need to heat the neutron source to extremely high temperatures. However, the reactions still occur relatively infrequently, and the resulting energy release is far less than the energy expended on accelerating the nuclei. Therefore, neutron generators cannot be used as energy sources. However, the neutrons produced in the reactions have valuable and practical applications. The authors of the article claim that the probability of spontaneous fusion reactions in hydrides of heavy metals, primarily palladium, is approximately 20 orders of magnitude higher than in gaseous deuterium. Furthermore, in specific locations where the metal's crystal lattice contains defects that lead to a higher concentration of electrons, this probability can locally increase by an additional 10 to the power of 10 times. The researchers suggest that, in the future, such defects could be introduced into materials artificially, much like how impurities are currently added to semiconductors to control their electrical properties. Unfortunately, even increasing the probability of spontaneous fusion reactions by 10 to the power of 20, 10 to the power of 30, or even 10 to the power of 35 times would still not suffice to initiate cold nuclear fusion with adequate intensity. We would still fall short by about 10 orders of magnitude. The authors acknowledge this limitation, but propose that other effects could be leveraged to further amplify the intensity of these reactions. As discussed earlier, fusion reactions, like all quantum mechanical processes, are probabilistic in nature. This is why fusion can sometimes occur under conditions where it theoretically shouldn't, as in the case of the sun's core. Conversely, because fusion is a probabilistic process, there are times when it won't occur even under conditions where it theoretically should. Put simply, even if we accelerate atomic nuclei to speeds, or more precisely, kinetic energies, seemingly sufficient to overcome the Coulomb barrier and bring the nuclei close enough together, not every such close encounter will result in a reaction. Only some of these nuclei will fuse. In other words, even under ideal conditions, the probability of a reaction occurring is never 100%. In essence, there exists a baseline probability threshold for fusion reactions, which is not directly influenced by external conditions, but is instead determined by the intrinsic properties of the nuclei involved and the outcomes of their fusion. What if we could somehow reduce these limitations and increase the probability of initiating fusion reactions? In this case, the reaction rate would not only intensify under favorable conditions, but also become more likely under unfavorable ones. One such effect is the phenomenon of intranuclear resonance. As early as 1945, American physicist Egon Bretcher discovered that the fusion reaction of helium from deuterium and tritium depends on temperature, or more precisely, on the energy of the colliding nuclei in a nonlinear manner. Initially, the reaction rate increases, then peaks at an energy of about 100 kilo-electron-volts, and subsequently begins to decline. An even more intriguing scenario is observed in another reaction, where a boron-11 nucleus fuses with a proton. The product of this reaction is a carbon-12 nucleus in an excited state, which, within a very short time, decays into 3 helium-4 nuclei. As the kinetic energy increases, the probability of this reaction occurring rises steadily, but at a component energy of approximately 600 kilo-electron-volts, equivalent to a temperature of about 7 billion degrees, a sharp peak in reaction intensity emerges. Beyond this energy, the intensity decreases again before resuming a more gradual increase. This sudden increase in reaction intensity at specific component energies is what's known as intranuclear resonance. We won't delve into the nature of this phenomenon today, but I'll mention that it's directly related to the energy required to form the intermediate excited state, helium-5 in the case of the deuterium-tritium reaction, and carbon-12 in the boron-proton reaction. Unfortunately, for both the deuterium-tritium and boron-proton pairs, the resonance energies of these reactions lie in a range corresponding to extremely high temperatures, achievable only in thermonuclear fusion setups far more powerful than anything we currently construct. But what about the deuterium-deuterium reaction? Here, the situation becomes interesting. Its reaction intensity curve shows no peaks. Yet, all indications suggest that such a peak must exist, though we cannot observe it, perhaps because it lies in an energy range that we have not yet studied. Indeed, certain calculations, cited by the authors in their paper, suggest that this peak for the deuterium-deuterium pair might occur at an energy of 23.8 electron volts, corresponding to a temperature of 276,000 degrees. It's significantly higher than room temperature, but at the same time, several orders of magnitude lower than the temperatures required to initiate thermonuclear fusion. For this reason, there are currently no experimental data confirming whether reaction intensity at such temperatures increases from being vanishingly small to merely very small. The authors of the paper believe that some experimental evidence does point to the existence of this previously unseen peak. For example, the fact that, in the range of thousands of electron volts, the lowest energy range for which we have experimental data, The reaction level is slightly higher than theoretical calculations would suggest. This may occur because the high-energy tail of a resonance peak located in the range of tens or hundreds of electron volts extends into this region. Presumably, at this peak, the probability of fusion reactions occurring should be about 10 to the power of 7 times higher than away from it. That's not much, but considering that theoretically, we've already gained 25 to 35 orders of magnitude by embedding deuterium nuclei into the crystal lattice of palladium, it might turn out that we either achieve the desired effect and finally initiate cold nuclear fusion or come within arm's reach of doing so. However, there's one small issue that the authors of the article sidestep. As I've mentioned, the hypothetical resonance energy of 23.8 electron volts corresponds to a temperature of 276,000 degrees. In other words, this so-called cold nuclear fusion isn't so cold after all. Theoretically, though, there's another way. We could selectively deliver the required energy to small regions using powerful lasers. But this brings another problem. Lasers, especially highly powerful ones, typically have low efficiency, and we might end up expending more energy on exciting the nuclei than we gain from the reactions. The authors of the article don't address these issues. They're primarily interested in the theoretical possibility of achieving cold or conditionally cold nuclear fusion. The next step is straightforward. It remains to determine whether the deuterium-deuterium reaction truly has this hypothetical resonance peak at 23.8 electron volts. Even if it turns out that this peak doesn't exist, or that its practical potential cannot be realized for one reason or another, the authors propose a third effect, or rather, a group of effects, that could theoretically increase the probability of fusion reactions at low temperatures. To understand what they mean, we'll have to dive a few steps deeper into the intricacies of quantum mechanics. From a quantum mechanical perspective, nuclear fusion can be viewed as the transition of a system from a state of two atomic nuclei with higher total energy, and thus mass, to a state with lower total energy and mass. The probability of such a transition is determined by the energy difference between the two states. Simply put, for the transition to occur, an active energy release from the higher energy state must take place, and the probability of this transition is determined by the likelihood of such a release. In quantum mechanical terms, the probability of nuclei undergoing fusion depends, among other factors, on the likelihood that the resulting fused nucleus can release its excess energy. And this likelihood, in turn, depends on the mechanism by which the nucleus sheds that energy. During the nuclear fusion involving two deuterium nuclei, the energy is typically released as the kinetic energy of the reaction products, a helium-3 nucleus and a neutron, or a tritium nucleus and a proton. In rare cases where helium-4 is formed as the reaction product, energy is released in the form of a gamma photon. These mechanisms of energy release, or reaction channels as physicists call them, determine the reaction's probability. However, if the system has access to additional reaction channels, energy can be released more easily, increasing the reaction's likelihood. The authors of the article argue that the presence of metal atoms constituting the lattice near deuterium atoms provides the nucleus with additional mechanisms for releasing energy, such as through electromagnetic interactions between atomic nuclei. On the atomic and molecular level, these processes are well understood and studied. One example is the so-called fluorescence resonance energy transfer. In nuclear physics, such processes are much weaker and less explored, but they are expected to occur nonetheless. Group effects, where the same processes occur with a large number of neighboring nuclei, should also contribute to enhancing the intensity of nuclear fusion reactions. An analogy can be drawn with a well-known phenomenon, stimulated electromagnetic emission. When we excite an atom by imparting energy to it, causing one of its electrons to transition to a higher energy level, the relaxation process of the atom, during which it emits a quantum of electromagnetic radiation, is probabilistic. The atom will remain in its excited state for some time before transitioning. However, If a photon with the same wavelength as the one the atom is about to emit passes nearby, the emission will occur instantaneously. In other words, if we take a group of atoms in an excited state, once one of them emits a photon, it triggers a chain reaction, causing others to transition to their ground state. This is the principle behind lasers. As with fluorescence, the nuclear analogs of these processes are much weaker and less understood. Nevertheless, certain experiments suggest that these effects not only can exist, but must exist. For instance, in one experiment, iron-57 atoms were excited to a state with an average lifetime of 14 nanoseconds. However, when exposed to X-rays with a photon energy of 14.4 kiloelectronvolts, corresponding to the transition to the ground state, this lifetime significantly decreased. The authors of the article believe that properly accounting for quantum mechanical effects of this nature could increase the probability of initiating fusion reactions at room temperature by approximately 30 orders of magnitude. Combined with other methods of increasing this probability, the authors argue that it may indeed become possible to achieve the desired result, initiating nuclear fusion in hydrides of heavy metals at room temperature. As a reminder, achieving this requires increasing the probability by about 40 orders of magnitude. Essentially, to initiate cold nuclear fusion, according to the calculations presented in the article, it's enough to fully utilize any two of the three groups of effects mentioned, or to combine a little from each. On this basis, the authors conclude that cold nuclear fusion is indeed possible. Personally, I had mixed feelings about the article. The idea itself is intriguing. To determine whether this is feasible at all and whether it's worth investing money, effort, and time into research in this direction, or to finally classify cold nuclear fusion alongside perpetual motion machines and similar nonsense. And the authors conclude that it's too early to dismiss it, quite the opposite, in fact. At the same time, for my taste, the article contains too many ifs, perhapses, and maybes, as well as assumptions about how things might actually work in largely unexplored areas. Furthermore, the article offers almost no practical guidance on how to implement the proposed methods of increasing the intensity of fusion reactions. It's entirely possible that even if cold nuclear fusion could be achieved, the energy obtained might be so expensive that it would have little practical value. On the other hand, even if we fail to unlock nearly limitless sources of cheap energy, research in the areas outlined by the authors could lead to many valuable discoveries on their own. Once again, the analogy with medieval alchemists is fitting. While they never found the philosopher's stone, their quest led to significant breakthroughs, such as methods for distillation, crystallization, calcination, and other processes that are foundational to modern chemistry. Similarly, in today's video, we've done something comparable. By exploring the topic of cold fusion, we've gained deeper insights into a range of subjects in nuclear physics, quantum mechanics, and related disciplines. If you found this video interesting and useful, I'd like to ask for your support in helping our channel grow, either here on YouTube or through our pages on Patreon and Boosty. And all the necessary links will also be in the video description. Once again, a huge thank you to everyone who already supports the channel and to those who decide to join our sponsors today. That's all from me for now. Take care, dear friends, and see you soon in our next videos.